But good morning, good afternoon, good morning, good afternoon, good evening, wherever you might be. Welcome to Fireworks' first ever webinar series. We're going to actually have one webinar every month. We're also going to have office hours every month, a Discord AMA every month. I'll get more into those. The topic of today's webinar is fine tuning. And specifically, we are going to get to a demo of fine tuning with Fireworks. But I also want to kind of give a kind of a level set understanding of where does this concept of fine tuning, what role does it play in modern AI and modern LLM development? And for those of you who are new to Fireworks, again, for those of you who are new to even fine tuning in general, don't worry. I want you all to think of us and me right now specifically as people who are here to help you. We are here to answer your questions. We are here to get you up and running on the platform, building your own models, using our serverless inferences, whatever that might look like on Fireworks. We're here to help. So if you do have questions, even just about Fireworks in general, we do have time for open QA at the end. So I might not get to your questions immediately as I see them in the chat here, but I promise at the end there will be time to answer as many questions as possible. Okay. Someone's asking, will the recording of this webinar be published? Absolutely. We are going to be, so this is already getting recorded. So for just a heads up, we are going to be releasing the recording in a follow-up email, as well as the slides, by the way. So we are going to release both the slides and the recording, just so you have that information. And so you can look back on it later, but good question. Thank you so much. And Ryan Crow, or Crow, as I will call him from here on out, has also put a link to our Discord chat, our Discord invite. Our AMAs are going to be held on Discord. I actually have the link as well on the slides, so to see a little bit later. So the agendas in general for these webinars are going to follow kind of four basic bullet points. We're going to start by just I'll give you a basic sense of what's recently been shipped at Fireworks. I'm going to call out some announcements, call out some case studies that have been published, just a general kind of keeping up to date with what's new. Then we're going to get into our main core topic, and today's core topic is an introduction to fine tuning on Fireworks. Then I want to get into a demo. These demos are not going to be too long. In fact, if your calendar link says that this webinar is going to be 3 hours long, don't worry, it's not going to be. I'm going to get you out of here in time for lunch, at least if you're on the West Coast, like I am currently in sunny San Francisco. Oh, yeah, sunny San Francisco. So we'll be out of here in the next hour, maybe hour and a half, depending on questions. Do not worry. And that's how I want all these webinars to be. You're settled in, but I'll get you out of here before lunch again if you're on the West Coast. So we're gonna do a little bit of a mini demo, and I'll share my screen. I'm already sharing my screen, but I'm going to share the actual platform, some of the code that we're going to be walking through, and then at the end we'll do an open Q&A. And just I'll tell you right now, and I'll remind you again at the end. Like I said, we're going to have several events a month going forward. So these webinars are going to be monthly, every third Thursday of the month. And we're also going to have 2 office hours, which are going to be completely open. You can come ask any and all questions about AI. It does not have to be about fine tuning. It could be about anything that you want to chat about. Again, we are here to help you. That is the number one thing I want you to take away from these series is we are here to help. Okay, so who am I, by the way? Hi, I'm Sanan Ozdemir. It's very nice to be here. I am the head of AI education at Fireworks. And before Fireworks, which frankly I only joined last month to do the work that I'm doing now, I'll give you the long story short. I got my degrees in theoretical mathematics. I became a lecturer at Johns Hopkins, where I taught math and also machine learning. I built one of their first ever undergraduate machine learning courses back in 2014-ish, roughly. I switched gears into startup land. I started a company called Kylie.ai, which was one of Y Combinator's first ever generative AI companies back in 2015. We actually patented the concepts of agents, meaning generative AIs using Chrome extensions as tools back in 2019. I've also lectured for O'Reilly and Pearson. I've written several books. You can find them. Here's a picture of a few of them here if you want to find them. And like I said, find me, ask me questions both on X and LinkedIn. Come connect with me. Again, I'm here to answer your questions. Like I as head of AI education, I am head teacher in charge here. So you have questions, we get them answered for you. That is my promise. Okay, so let's go through our agenda today. We'll start with a very brief what we've recently shipped at Fireworks, and I want to kind of point out 4 main things. Or I guess five, five main things. I added a fifth one as of some breaking news as of this morning. So the first two are just kind of some case studies from other companies and other organizations who have been using Fireworks, namely in this case LangChain and Gumloop, who are using open source models. And for LangChain, they are talking about how they tuned their deep agents framework, which is an agent framework that LangChain puts out specifically for one of the top US open models, Nemotron. And Gumloop was basically putting out a post around how their use of open source models was really rising in the last month alone, and how much money they've been saving by making that switch across the board. New model alert, and there's always going to be new models coming in. It's one of the hard parts about staying up to date with AI. But in addition to some other models that are coming very very soon, one that I can definitely talk about is, or rather, it's already available. I should say, is Inkling from Thinking Machines. Again, as I was saying, kind of before some people showed up, I'm going to be spending this weekend doing some deep dive into Inkling, just because I have not really got a chance to get my hands on it quite yet. It's quite large. It's nearly 1 trillion parameters with a million plus parameter, a million plus token context window. So it's definitely up there in terms of size and usability. So I'm excited to get my hands on it. Breaking news alert: as of this morning, Fireworks has actually just announced their Series D funding round, placing our valuation north of 17 billion, if I'm not mistaken, and that's obviously very exciting for everyone at the company, but it's also very exciting specifically for us, because that really kind of puts a feather in the cap of our offerings on both inference and training are only going to get more and more robust. And part of this webinar series is to hear from all of you, like what are you trying to do, what are you trying to train, what would you like to see from the Fireworks platform, and that's going to really inform me and the rest of my team. What should we be building? And on that note, on our cookbook, which there's a link here, the QR code will also take you directly to our cookbook right there. That's where you're going to find a majority of our examples. I've actually added the case study that we're going to be walking through today in our mini demo on that GitHub, as well as 3 other case studies. And my goal is to add at least 3 or 4 case studies every month. So every webinar, you're going to see at least one net new demo from us. So again, if you have suggestions on what you want to see, tell us here, or frankly, ask us in our GitHub, or ask me on LinkedIn and X. Crow, thank you for putting the link in the chat. I appreciate that. All right, so let's talk about an introduction to fine tuning, and to get a sense of an introduction to fine tuning on Fireworks. I am going to have to walk you through. This is educational, folks. I am going to walk you through some of the key points of modern LLM development, and this kind of starts with this concept of there are 3 main phases of LLM development. We have what we call pre-training. Pre-training. We have what we have called supervised training, and then preference training. Now, a note on some terminology as we go forward. You're going to hear different people kind of put different names to the same things. For example, you will often, when someone says the 3 phases of the development, they'll say pre-training, supervised training, and then they might often call this last bucket post-training. And I think what's really easy to do is get caught up in that kind of terminology war, so to speak. But as long as you're being very specific about the techniques that you're talking about. So when I say these are the 3 phases of development, you'll note that I'm not necessarily tying each one to a specific technique, really, outside of the middle one here. But I'm trying to split them up into what you are trying to do to the LLM in each one of those phases. So I do want to walk through each one of these phases with some kind of visual examples of what it actually looks like to go through these phases. And we're going to start with pre-training. You may have heard this term just kind of thrown around casually in conversation when talking about LLM development. The idea of pre-training is that you are asking an LLM to effectively memorize and read as much information and data as possible, usually data from the open web, but that also sometimes includes proprietary data. In fact, a lot of this, not a lot maybe, but part of the secret sauce that AI labs have, behind the scenes, that includes, thinking machines today, that includes Anthropic, that includes, ZAI, the people who make these LLMs, part of their kind of what makes them different from each other is the data that they use to train these models. And that starts at pre-training. And the concept of pre-training is there's not really a task per se that the researchers are trying to teach the model to do. It's really more about read this, memorize this, internalize this, update your weights, update the actual, update yourself effectively so that you could regurgitate this information if I were to bring it up. So this is not a chatbot yet. No, it's when we walk through the three phases, we see more and more closer to what we would consider today to be an LLM off the shelf. But step one of making an LLM is pre-training. Read as much information as possible. In fact, the largest sets of data when it comes to training an LLM generally falls into the category of pre-training, because again, they literally mean read as much information from the open and closed web as you possibly can and just memorize this information. Because once that LLM memorizes that information, we can move on to step two of modern LLM development. And that's going to be called supervised training, or from now on, I will call it supervised fine tuning, SFT, because that's also going to be terminology that you'll see on our platform. Supervised fine tuning, for you machine learning heads out there, this is not a new term. This is frankly the supervised fine tuning you would have learned about decades ago. And it's this concept that if you show a machine learning model, of which LLMs are a subset of machine learning models, if you show a model an example of something, anything being done, supervised fine tuning is the act of updating the model to mimic the examples that you're showing it. Now, to turn it more towards modern LLMs, as we think about LLMs today, generally the thing that we are showing the models is a conversation. You show an LLM, this is what a conversation looks like. So if you're familiar with this format on the right here of messages, role system, role user, role assistant, this is that back and forth message standard that we've all pretty much become very familiar with, including a system prompt at the top. So when we talk about data for supervised fine tuning, when it comes to modern language models off the shelf today, this is the data that we are showing them. Now, as we'll see in a slide or two, this isn't technically exactly the data that we're showing the LLM. This is how we humans are going to be building these data sets for supervised fine tuning. It's also important to note when you're doing supervised fine tuning, and which by the way, our demo today is going to be a supervised fine tuning example. The examples that you show have to be, at least the model will assume that they are correct and complete. Meaning, you'll notice in this example, the last message is the assistant. Again, we are literally showing the LLM, I want you to react this way. I want you to respond this way when this conversation goes like this. It is a very rigid technique because the model is simply trying to mimic and frankly regurgitate the style, the tone, the quality of the examples that you give it. Now, that concept of rigidity will be kind of ironically a little bit flexible as we see some more examples, but it is generally considered, supervised fine tuning, SFT, is generally considered one of the more rigid forms of fine tuning because again, it has the model has no room to explore, try things. It's really LLMC, LLM do. So when to use supervised fine tuning, generally you are trying to coerce the model into producing a more consistent tone or format. And the concept of correct examples exists. And that might sound strange because some of you might say, well, of course there was. There's always a correct answer. Well, not necessarily. Sometimes there are better answers than others. And sometimes there is a single correct answer that you want the AI to say. And that what I just said, that line in the sand of there does exist a single correct answer versus there are multiple possible answers, but there is a way to at least rank which ones are better than others. That actual divide is going to be also the divide that we put between that supervised training and that preference training, that second and third bucket of LLM development. But as of now, we're still in SFT. We are training these things to look at correct examples of, in this case, conversations. So what SFT is not really going to help with, again, as I said, like preferences are, it's not a great use of SFT to teach a model new information. Technically speaking, it is possible. Do not get me wrong. It has been shown that you could use techniques like supervised fine-tuning to teach a model new facts. But like I said previously, pre-training is one of the more effective ways of teaching the model information by not showing it these fully formed chat, completions, these chat conversations, but rather just reading the raw data from the open internet. Now, kind of going one level deeper here, we're not going to go too deep, I promise, but under the hood, that message list that I showed you, like I said, that's the human form of what we are looking at. That's what the human sees when we create that training data, but it's not what the model sees. What the model ends up seeing is that list of messages formatted as a single piece of text. So what you're seeing on the right here is the exact same conversation from the slide before, but this is a real template. I took Qwen 3, which is an open weight model. I took Qwen 3's chat template and I converted that list of messages into what Qwen 3 would actually see in its when it is training and when it is actually performing inference. Now, to be clear, this is also true for OpenAI, for Anthropic, for Google's Gemini. This is just how LLMs see the message lists that we create. I can only do this for Qwen because Qwen is an open model. I don't technically know OpenAI's chat template to my knowledge. I don't think we know exactly what this text format would look like for OpenAI. Now, caveat to that, technically I have seen it when I saw one of the first versions of ChatGPT in 2022. I did technically see it on a board. I don't quite remember it, but my point is there is a chat template at OpenAI that they use. It's just not an open chat template, so I can't just grab it online and then convert my messages into that format and then be able to look at it as a single string like I can with Qwen. So by showing it this piece of text, it in a way resembles pre-training. I am showing the model a piece of text. This text just happens to be always in the exact same format over and over and over again. While as in pre-training, if I'm showing it Wikipedia, I'm showing it a news article, I'm showing it these blog posts that I got on the open internet, they're all going to be in relatively different formats, relatively different styles and tones and everything. So there's not a lot of structure. Supervised fine-tuning is very much a lot about structure. You're teaching the LLM the structure of a conversation so that when it is asked to extend that conversation, it knows what it's supposed to look like. It's supposed to start with a system. It's supposed to go back and forth between a user and an assistant. That format is learned during supervised fine-tuning. Quick history lesson, because that's everyone's favorite, I know. There's a model called Flan T5. And if you've never heard of it, I do not blame you. It is a model actually made by Google originally in 2020. It was their T5 model. Their text-to-text transfer transformer is what T5 stands for. Sorry, 2019. I was mistaken, for 2019. Now, the 2019 version of T5 was only pre-trained. It had read, I believe, Common Crawl, which is a very common data set of pre-training information, but that was it. 3 years later, in 2022, actually, if I'm not mistaken, a couple months before ChatGPT was released in November, roughly, Google put out a second version of T5 called Flan T5. I do not remember what Flan stands for. I wish I did, but there's a link to the paper there that probably says it. But Flan T5 took it a step further and added the supervised fine tuning step. So keep in mind, back in 2019, 2020, those three phases of LLM development, for the most part, did not exist. Does that mean no one had ever done that kind of recipe before? No, but it was just not the standard way of training these language models yet. It's about to be in roughly 2022, 2023, but it's not because of Google, and we'll see why in just a moment. But what was interesting was even just with those two steps, pre-training and supervised fine-tuning, the Google researchers noticed that the model would be able to generalize that instructional behavior to unseen questions and tasks. For example, they would teach the model how to translate, let's say, English to French, but they never taught it to do English to German. But by giving it so much just open information from the web and teaching it the general style of conversations and instruction following, they would find that the model could also translate into other languages, even without being explicitly trained to do so using supervised fine-tuning. So this concept of generalizing to unseen tasks, this is sometimes referred to as emergent behavior, but kind of more formally, I would diagnose that as a generalization of instructional behavior, because the core tenet of machine learning engineering, which again, this technically is machine learning engineering, is you are training a model to not just mimic the data that you're showing it, but you're also testing it on its ability to generalize that knowledge to unseen data. When we get to our fine-tuning on fireworks section, I'm going to reiterate that concept and very specifically how you can test for that generalization using your data. So that's pre-training, that's supervised fine-tuning, sometimes referred to as mid-training or instruction training, but I will call it supervised fine-tuning as kind of its more formal name as phase 2. Phase 3, preference training. What makes preference training different from supervised training is mainly in the techniques, because the goal is to move away from do it exactly like this. That's phase 2. Phase 2 is do it like this. Phase 3 is we're going to give you some flexibility. We're going to start to teach you the gray areas, the nuances. That nuance, that gray area is in theory impossible, but nearly impossible to teach via supervised fine-tuning. Because to teach that nuance, you would, in theory, have to have examples for all of those nuances ahead of time. And that is frankly intractable. That is a very difficult problem to solve. So instead of generating an example for every possible gray area or nuance, preference training takes over. And the most common algorithm or technique, I'll call it, for preference training is called reinforcement learning. Now, I'll tell you right now, definitely on the scope for a future webinar is a deeper dive into reinforcement learning specifically. But for today, a very, very quick recap or just kind of intro to reinforcement learning is that instead of showing the AI correct examples, there are no labels in reinforcement learning. Instead, in fact, I'm going to do my best to, I should have a, no, I have a, this works, right? Oh, no, it's not working for some reason. My pen, usually, I'll have to figure that out a little bit later. But reinforcement learning, the way it works is actually on a loop. So the idea is reinforcement learning, you ask your LLM. Now, terminology note, classical reinforcement learning existed before the modern LLM. The term of art for the entity that was being trained was called an agent. So when I have an image that says agent on it, that's not necessarily an LLM with tools like we would call an agent today with a harness, Cloud Code or deep agents, something like that. I'm using agents here as a term of art in reinforcement learning. I know we can do a little better with our terminology, I am aware, but I'm just simply pointing out to you that these are the different ways of using the same words. So the loop of reinforcement learning goes, the agent in reinforcement learning will observe. It will be given a state, i.e., it will be given a prompt, a task to do, and but not the answer. That is very key here. It is not given the answer. It is only given the task, the context, if you will. The action that the agent will take is solve the task. If it is an actual LLM with tools, you may call your tools. If you have a sandbox, you may work in that sandbox. If you have neither of those things, you may speak. You will generate a response to my question. That creation of the output has a term. It's called a rollout. And in fact, you might see that term a lot more now that I've said it and kind of put it in your brain. The rollout is the LLM's completion of that task with or without tools or content or sandbox, whatever it is, but some completion of that prompt/task. The key part here then becomes the reinforcement part of it, if you will, is that once the agent is done with its rollout, some system, that something has to tell the agent how well it did, or vice versa, how poorly it did. That's called a reward. And the reinforcement part of the loop is that when the system gives a reward to the rollout, the model is then updated in an effort to achieve higher rewards the next time around. Now, what gives that reward? That's a great question. I'm sure it's on some of your minds. And it could be a lot of things. And again, I want to have a dedicated reinforcement learning webinar a little bit later. But for example, a lot of people will use what are called verifiable rewards. You may have seen the term RLVR, reinforcement learning from verifiable rewards. That's a fancy way, basically, of saying it is deterministic code that will tell whether or not, literally a regex. A regular expression would be a verifiable reward. Did the LLM at any point output text that matches this regex, yes or no? That is a verifiable reward that very often is used in reinforcement learning. In fact, that was a very big advancement from the DeepSeek folks on reinforcement learning from verifiable rewards. You could use another LLM as a judge to give rewards. That's totally possible as well. As long as something gives a scalar a single number, and there's caveats to the algorithm here, but generally speaking, as long as the system can give a reward that's positive when it's good, negative when it's bad, you have what you need to run this reinforcement loop. History lesson number 2, proto-ChatGPT. For those of you who had not been following OpenAI since their early days before 2020, like me, this is actually literally a history lesson, because this screenshot that you're looking here is in one of my past books from 2021. Or no, that's not true. From like 2023 or 4, roughly. And this model that I'm referencing does not exist anymore. One of the fun parts of using closed source models from companies like OpenAI is that one day they go away and you'll never have access to it ever again, because it's not going to most likely ever get open weighted. So the model that you're looking at, both on the top and the bottom, technically do not exist anywhere publicly, and you are not allowed to talk to them anymore. But I was allowed to talk to them a couple of years ago, and it shows an interesting story. GPT-3, the generative pre-trained transformer, its third iteration, was released in 2020, and it was mostly used in research settings, some applications. I was, for example, not fine-tuning, but I was using GPT-3 at my company at the time. And it was just a pure language model. So this is, again, real screenshot. When you asked it, is the earth flat? It wouldn't really answer my question. It was just a pre-trained language model. It had not gone through any form of supervised fine-tuning of conversational structure, nor had it gone through any form of reinforcement learning as preference training. 2 years later, in 2022, that's the year that ChatGPT was released in November, but before ChatGPT was released, a select few developers, myself included, were invited to kind of behold a proto chat GPT, which they refer to as instruct GPT. And in their API, they had eventually called this, I believe, DaVinci was then the original name. But I think they called it instruct GPT before they called it DaVinci. Um, After it had gone through supervised fine tuning and reinforcement learning, which I label here as reinforcement fine tuning, I'm going to use those terms roughly interchangeably from now on. It would respond to that question in a not just in a direct way, like yes or no, but in a more friendly, informal, casual way that would be what users ended up wanting to see from their models. Fun fact, the original Instruct GPT that was trained on the process that OpenAI called RLHF, reinforcement learning from human feedback, which is really just reinforcement learning where the reward model was actually supervised, fine-tuned from human preference data. So that's all that means. Human feedback is OpenAI would take literal human beings, make them pick, this response was better than that response. This response was better than that response. They would train an LLM using supervised fine tuning to mimic human feedback. And that trained LLM became the reward model for GPT-3. So they had all kinds of fine tuning going on. And it wasn't just the GPT model that they were actually fine tuning. The reward model was also being fine tuned as well. That original Instruct GPT was not even a chatbot. It was literally done as a single input in, output out, one time. One input in, one output out, and that was it. There was no semblance of a conversation. It was fine-tuned just as input, output, prompt, response, as we used to call it. Prompt response pairs, and that evolved into the chat format we know and love today. Okay, so this slide you will probably see again if you come to a future webinar on reinforcement learning. But when it comes to preference training, the world of algorithms and techniques kind of explodes more than pre-training and supervised fine-tuning. Here's a few popular ones today. PPO, proximal policy optimization, that's actually the classic, if you will. That's the algorithm that OpenAI used in 2022 to train their Instruct GPT and their original Chat GPT models. For what it's worth, PPO is not really so much in use these days. The variations of PPO are, do not get me wrong, but PPO as OpenAI originally used it in 2022 is not a very commonly used algorithm anymore. It's still used, and that's still very much an option, but more widely used would be techniques like DPO, direct preference optimization, or GRPO, group relative policy optimization. GRPO is actually a technique popularized again by the DeepSeek team for DeepSeek R1. So in that same breath that they were kind of talking about RLVR, verifiable rewards, GRPO became their technique of choice because it was a very natural way of combining the verifiable rewards at scale. But again, I will save that for a future webinar because I think it's actually quite interesting. And there's more. There's KTO, ORPO, odds ratio preference optimization. There are, conservatively, dozens of algorithms to choose from in the world of preference training. I'll give you a sneak peek into one of them, and that's DPO. And DPO is actually fascinating for many reasons. Most prominently in that it's a preference technique, but it is not technically reinforcement learning. In fact, the authors of the technique, and I'll do my best to always cite my sources here so you can read the paper if you'd like, they actually make it a point to say DPO is effectively a hybrid of the best of both worlds of reinforcement learning and supervised fine-tuning. The idea, and again, literally taking a screenshot from their paper here, is that instead of reinforcement learning from human feedback, in which you train a reward model to mimic human feedback, use that reward model to give rewards to an LLM, that's really complicated because first you have to train the reward model, then you have to train the reinforcement learning technique. You have to do all those separate steps. What if you could do it all in one step? So they basically, and again, I'm going to hand waving away a lot for a second here, is that they're instead of training that reward model, the DPO, the direct preference optimization algorithm, would put that objective of increasing preferred responses directly inside of the model's weights itself. So increase the probability of the chosen response relative to the rejected one. Chosen, rejected, preferred, non-preferred. These are basically synonyms for the same. As DPO demands pairs of data in which you have the same inputs, but the outputs are different. And you don't have to put a reward to them. You don't have to say this one is a 5, that one is a 3. You simply have to say this one is preferred over this one. There's a lot of caveats there on how you want to structure that data, because again, you can get lost in the nuances, because if there's a big gap between preferred and non-preferred, then you kind of want to fill in the gaps of, well, this is great, this is terrible. Is there such a thing as pretty good? You want to make sure you're filling out that space. People are also posting links to our blogs around DPO as well. I appreciate that. And so once we can get through these 3 levels of training of an LLM, this is reproducible. I mean, like I said, this is pretty much the same technique that most labs do today. In fact, in one of my recent books, I actually took this as a test and said, well, I'm going to make my own LLM. So I made Sanan's attempt at wise yet engaging responses, i.e. Sawyer. And what I did was I took a model off the shelf that was already just pre-trained, a Llama 3 8 billion model that was only pre-trained. So when you asked it a question like, who's the first president of the USA, it would not directly answer my question. It would say something like, what role did he play in the American Revolution? George Washington. He was a great general. It's kind of rambling a little bit there, but that's not unexpected, because again, it has not yet learned the conversational format on how to respond in a preferred way. After I put it through supervised fine tuning, then it would actually respond to my questions, albeit a little bit bluntly and directly. And after reinforcement fine tuning, by showing it what is good, what is bad, what is better, what is worse relative to one another, I could move. It was still answering my questions, but in a way that I would kind of accept it more from a commercial standpoint. It's more warm, it's more engaging. That preference training is not teaching the model new information. It already knows who the first president, it always knew who the first president of the USA was, theoretically. Only after SFT, supervised fine tuning, can it answer a question in context, and only after preference training with reinforcement learning, which, by the way, in my book, I had called it reinforcement learning from feedback, RLF. That's why the acronym on the right says RLF. That's from one of my books from a couple of years ago. That it would also be synonymous with RFT. So there's a lot of acronyms flying around, I know, but that is RFT. But after RFT, it still knew who the first president was, but now it knows how to answer in a more warm way. Now, there's more technically phases if you want there to be. For example, there is such a thing as continued pre-training, which is the act of effectively tricking an LLM into doing more pre-training, even after it's already gone through supervised fine-tuning and reinforcement learning. Same model, Sawyer, when I had gone through all 3 of those phases, I asked it, what's an LLM? And it told me it's a postgraduate degree taken after a law degree. That's actually true, by the way, if you didn't know that. The royal we stole that acronym LLM from the legal side of the world, which is a Master of Laws degree. It stands for, which was LLMs. So it's not wrong per se, but I wanted it to have more knowledge of modern LLM vernacular. So to do that, I basically made it read my book, not in a conversational format, not with reinforcement learning, like in pre-training, just read my book a couple of times on LLMs. And then all of a sudden, it still remembered how to be warm, how to answer a question. And now it has that added knowledge inside of it. So when we say fine tuning or training, what we are referring to in kind of most conversations is the act of changing the weights of a model off the shelf with a specialized data set. Those models off the shelf usually are at least pre-trained, if not already have gone through supervised fine-tuning and reinforcement fine-tuning. So the methods I've been talking about, supervised fine-tuning, direct preference optimization, reinforcement fine-tuning in general, even continued pre-training, these are in theory not in theory, these are all practically all forms of fine-tuning, taking a model off the shelf and updating its weights. Now, in more casual conversations, when most people say the words fine-tuning, they're often referring to something along the lines of supervised fine-tuning, a preference tuning like DPO, or general reinforcement learning or reinforcement fine-tuning. Now, to do a proper, so to speak, fine-tuning act, you generally want to walk through these steps. Again, generally, this is going to differ from organization to organization, but you are going to have some data. Now, whether that's labeled data or not, again, labeled meaning you have a complete correct conversation like supervised fine-tuning, or for reinforcement learning, you have a bunch of inputs, context, environments that for the LLM to roll out with, and a reward mechanism ready to go. Generally speaking, and I'll kind of I'll gear this towards supervised fine-tuning for the sake of our example today. You take your labeled data, your complete conversations, and you want to split that up into three parts: training, validation, and testing. The split ratio, it can differ from person to person. Sometimes people will do like 70, 15, 15, or 80, 10, 10. But for now, it doesn't really matter what that split is. Some people will have strong feelings about it, some people won't. But you want to make sure that your training set generally is the biggest one, because what's going to happen during fine-tuning is that you're going to update the model's parameter weights using the training data. That is the only part of the data the model is allowed to read and update on, so that it can mimic it, so that it can learn how to get higher rewards. Every so often, usually we call that every epoch, which is one pass of the training set, you halt the training, you pause training for a second, and you say, just to make sure we're on the right track here, I'm going to give you a pop quiz. That pop quiz is the validation set. So the model is not allowed to learn from the validation set. It's a test. You test it on the validation set every so often. And again, from what I said earlier, to see if the model is able to generalize to new data, so that you're making sure that it's not just regurgitating and memorizing the training data. We call that overfitting, but it's actually able to take what it learned from the training set and apply it somewhere else without having to be trained on that data. So you just kind of make sure, because sometimes this loop, this active fine-tuning, I mean, for bigger companies, this literally could take days, if not weeks. And I mean that sincerely. Now, our example will run at about 20 minutes. Don't worry. But this is a real concern, especially if you're going for hours, days, or weeks, is having some way of knowing, is this even on the right track? Once you're done with that entire loop of training and validation, ideally, you have a test set waiting for you. So the model has never seen this test set yet. It's a final test, the final test as opposed to the pop quiz of the validation set, to make sure here's a second bit of unseen data. How well are you going to do on this? For a mental model, benchmarks, when you think of a benchmark like software engineering benchmark, SWE bench, or Tau squared, a tool calling benchmark, think of those like public test sets. Those are public test sets that we all share and are aware of, so that we can compare our models apples to apples. And internally, if you're building models, you also want to have that sense of an internal benchmark, an internal test set, so that team A, who is working with this kind of model, this technique, versus team B, who's working with that model and that technique, they at least share a test set, a train validation test data, so that they're training on the same thing for the most part. But more importantly, they're testing on the same unseen data. So you have that internal benchmark to really prove which of those teams is more on the right track. So when you even want to consider fine tuning as an option for your organization, there's frankly more than I can fit on one slide, but to kind of consolidate into a few key points, if you're already prompting and doing techniques like retrieval augmented generation or RAG, which I'm willing to bet most of you, if not all of you, are already doing, there will be a point where those techniques will plateau. And that doesn't necessarily mean fine tuning is the correct next step, but it is a solid indication that it's time to start thinking about these techniques that not just update the systems around the model, but the model itself might need to get updated. Or you might have some behaviors that your prompts are not really able to reliably enforce. To put some names on this, perhaps you have a regiment of how you want the AI, your agent, your LLM with tools to call your systems. And you say, don't do this when this happens, but do this when that happens. If there's a lot of rules going into the prompt, you may notice that sometimes your LLM won't follow them 100% of the time. So fine tuning would be a one way of encouraging, almost in a way enforcing those rules by either showing them examples of what to do or punishing them in a reinforcement learning sense for breaking those rules. And then there's what I would argue the more common bucket of fine tuning reasons, which is efficiency, what I would call kind of efficiency. Someone's comments about RAG and BM25 and grep. There's also what I would call efficiency fine tuning, which is really, I want this behavior and my frontier model is fine at it, but I do it so often, I need it to be a little bit cheaper, a little bit faster. And if I can squeeze some performance out of an LLM, that would be a cherry on top. And that kind of efficiency fine tuning, like I said, is one of the more common introductions to fine tuning that most people have. In fact, that's effectively going to be our example today, is a form of efficiency fine tuning using supervised fine tuning. Now, if you're already finding that your model works good enough, well enough with your prompting and RAG, like I said, fine tuning is not for everyone. That's not the point of this, is to convince you have to start fine tuning today. In fact, if you think you might want to fine tune, ask me, quite frankly. I'm happy to kind of walk you through that answer or kind of what my opinions would be. It's not necessarily for every task and for everyone. And if your specific problem that you're trying to solve is just knowledge freshness, for example, like, oh, my model needs to be up to date with our new product line or new customer support FAQs. Fine tuning is not really an efficient way and a fast way of introducing new information into a model. It can be done, but what's faster is to simply use retrieval augmented generation, give it a way to look up those documents instead. So it's not necessarily the answer to everything. Okay, now I promise you this is going to be kind of the most math heavy slide. In fact, I'm not going to really walk through any of the math, but I do want to make a point specifically at Fireworks fine tuning. There's a lot of work that's being done under the hood behind the scenes to make fine tuning as efficient as possible. One way that we do this, and this is not necessarily proprietary to Fireworks because this is an open technique that people use, is called LoRA, low rank adaptation. You may have heard of this before if you were looking around fine tuning in general. Low rank adaptation is actually I'm going to be honest with you, I would argue that more than the transformer in 2017, which is the backbone architecture for virtually every LLM you've ever heard of in your life, more than that, I would personally make the argument that LoRA has a shot at being the most groundbreaking deep learning finding in the last 10, maybe even 20, 30 years. Because what low rank adaptation does, what LoRA does, is it provides a way to train any deep learning model, not just the transformer, any deep learning model can be trained more efficiently on smaller or even single GPUs by employing a trick. And the trick is, instead of trying to update these huge weight models inside of the deep learning model architecture, instead, it fine tunes what we call an adapter. It's basically a sidecar of weights that represent the update to that matrix itself. So you instead tune that update to the weights. So the model is frozen. The actual huge model that you're training doesn't actually change. It's frozen. What you are fine tuning is a little sidecar of weights next to it that represent the change in the model after fine tuning. So when you're only training those small amounts of parameters, you get, I mean, it's hard to put numbers to it because it kind of changes depending on the size, but you get more realistic actual it's so much cheaper and faster, quite frankly, to fine tune this way. So much so that we generally don't recommend people start with what we call full parameter tuning until they've at least tried a few rounds of LoRa fine tuning, which is completely built into the product, by the way, at Fireworks. So if you're going to do some fine tuning with Fireworks, you're most likely going to be using LoRa. But there are many other techniques under the hood I'm not going to get into today, but this is just one of many. And also, you can't fine tune everything, unfortunately. You can only fine tune a model for which you have the weights you have access to, or the provider explicitly gives you that option. So for example, Anthropic does not offer direct fine tuning outside of a very niche use case of a Haiku supervised fine tuning, but only on Amazon Bedrock, from what I from what I was able to look up as of today. OpenAI has fine tuning, but they are actively winding it down. I believe January 2027 is when they're going to stop allowing even existing users of fine tuning to keep fine tuning their models. Gemini actually does offer only supervised fine tuning on Vertex AI, but no other type of fine tuning. So you don't have access to be able to fine tune any model out there, unfortunately, but you can fine tune any open model. Now, if you want to fine tune through Fireworks, you'll be able to fine tune the models that we have in our catalog, which I'll show off when I share my screen here. But as a fun kind of fact here, you might even find that on Hugging Face, which is the world's largest repository of open models and data sets, among other things, that some models and providers like Google and Gemma, their open weight model, they'll provide both the pre-trained version on the top here and the one that has been instruction aligned with reinforcement learning and supervised fine tuning. They'll release both of those models. The idea being that, well, if you're trying to just use a model that has a lot of information inside of it, but has not yet been trained to be a chatbot, use the pre-trained version. So this kind of comes back to the idea that pre-training is one of the most powerful phases because that's where the model learns pretty much everything it's going to learn. Everything that comes after is just teaching it to be a proper chatbot, a usable and useful chatbot using the knowledge it learned from pre-training. Okay. This takes us to our demo, and that's going to take us to open questions, and we'll be able to call it a day. So our demo today is going to be a supervised fine-tuning, specifically a vision supervised fine-tuning. So when I do these demos, I'm going to try to walk through in a pretty structured way what the task is, what the data is, what the model is, just to kind of give you a sense for what we are trying to do. And more importantly, at least for me, is I hope that as I perform these demos over our next webinars and you look through our cookbook, the goal is for you to look at one of these demos and say, that kind of sounds like what we're doing. I mean, replace receipts, replace X with Y and replace, D with F. And then it's basically what we're doing, right? I hope that happens, because if that happens, that means you should be able to take my code, make relatively small changes to it, and be able to use it for yourself. That's the vision here. So like I said, if you have examples of what you are trying to fine tune and what you would like to be able to do, let me know either here or on LinkedIn or on X, wherever that might be, on office hours next week, wherever that is. So our task specifically today is going to be to convert receipt images into a structured JSON like this, which includes the actual coordinates for where this information is exactly on the receipt. So if you have a task like, I have images that I need to extract and turn into a clean and accurate, consistent format, this is going to be right up your alley. So our data to do this, we're going to use an open data set called CORD, the Consolidated Receipt Data Set for Post OCR Parsing. There's a link to it on the bottom right of their GitHub. There's also a public version of it on Hugging Face. That way, again, you can follow along if you want to run this code. There's 1,000 labeled examples split up already into a 800, 100, 100. They have several classes or categories of types of receipts, depending on where that receipt is from. And also, for what it's worth, I'll do my best to always call this out. The license is free to use, modify, and deploy commercially, meaning you are allowed to train on this data set and use it and ship that model as long as you credit the CORD authors when you do so. So very open license for this kind of work, which is great. Our model is going to be Qwen3 VL Vision, 8 billion parameters, which squarely puts this in the small category, I would argue, a small LLM. I know there's SLMs and the terminology can be a little fluid, but 8 billion parameters for me is under the mid-range. So I put it as small LLM category. Why did I choose this one? Well, first of all, it's a vision model. It already has the capability of taking in an image, which I kind of need, of course, because I'm using a vision data set. It's also tunable on Fireworks. So, it's definitely on, it's on the list. I have the pricing here as of today at the very least, and fine tuning pricing as well, which I'll come back to how much this thing costs by the end. Now, before I share my screen and show you the code and kind of what it looks like on our platform, a couple of terms that you're going to see that I want to explain ahead of time, just so you can, and I'll show it again when I share my, or when I show the platform at the very least. A loss function is a term of art in deep learning in general, always has been. The idea of a loss function is that it measures, it's an error quantification. A loss function tells you in numbers how wrong your model is when it is predicting things. So while it is training, you're basically calculating the loss, meaning you check the model's error when predicting this data, and the goal is to have that error go down. So what you're looking at is the actual loss values from the example that we're about to do, where there's a training and evaluation. So evaluation is the validation set that I mentioned earlier. I'm measuring both. You want to see both of those go down, because it's very possible that training loss goes down, because if training loss does not go down, you have a fundamental issue with your model and architecture, because that's the data it's training on. If it's not getting better at the data it's training on, something is wrong. The validation loss is really what you're looking for, though, because you want both of those to go down. You really want validation loss to go down, because remember, it doesn't learn from validation loss. It is a pop quiz. So if that's also going down, you have a good sense that your model is not just memorizing the data, the training data, it's also generalizing it to the validation set. And that's good news, because that is more likely that when you show it new data, it's going to be able to predict it well off of the training. A hyperparameter is a catch-all term that basically refers to levers and settings that you can set before you actually activate your training. So these are not learned from data. These are things a human or an AI would set ahead of time. There are many of those. I will call out two. Epochs, which I mentioned earlier, is a number. It's an integer generally, refers to how many times you want the AI to go through the training set. Generally speaking, you want to do at least 2 or more epochs, meaning you want the AI to be able to run through the training data twice. If anything, to kind of prove, to show to the human, to the person evaluating the fine tuning, that when it got to the second pass of the data, as it goes through it again, it is actually, in fact, doing it better the second time around. In our case, I believe we do 6. And the amount of epochs that you choose Again, in our 201 fine tuning webinar that we will eventually do, that's an actually harder question to answer than you might think, because there's not really a good formula for how many epochs you should run. And I'm not even considering the budget you might have for time and in compute, but there's not really a great formula for how many epochs you need to run. What a lot of people will do is run for more epochs they think they need, and periodically save the model, the checkpoint, the model, save the versions of it as you go, so that you can bring them back, so that if training goes badly later on, you have a snapshot of when it was at its best before it got worse. Because here's the thing, if there is such a thing as fine tuning for too long, in fact, learning rate is one of the ways you control that. Learning rate is basically a way of saying, how fast will these updates happen? How big are these updates every single time we do that update? And if that learning rate is too high, training will destabilize, meaning it might get better at first, but then it'll get even worse than it started. But if your training rate, or sorry, your learning rate is too small, the model will barely learn anything. You're just kind of wasting everyone's time and money waiting for this thing to get better. So part of machine learning engineering and part of this experimentation is going to be figuring out what is the right set of these hyperparameters. People on staff at Fireworks, myself included, having trained for some people dozens, for others hundreds. I'm in the dozens. We have people on staff who have trained hundreds or thousands of these things in their lives. This is a lot of empirical evidence. This is a lot of, well, when I did this model for this data and at this size, these were the best hyperparameters. Maybe we start there because this is a pretty similar problem. A lot of this is actually experience and learning from those experiences. Okay, enough yapping. Well, I am going to yap still, but enough yapping with slides. Let's yap with code. All right, so I'm going to go ahead and reduce my slides here. And what we're going to do, so the code we're going to look at comes directly from our cookbook. There should be, I'm going to go ahead and put a link to the cookbook. I'm sure someone already has, but just in case. I'm going to link to our cookbook in the chat here. Great. And if you do want to follow along, of course, you can follow along code-wise, or you can follow along after the fact with our recording. No problems. To find the case studies, I'll tell you right now, you want to go to training, where my mouse is here. You want to go to training. And then in training, if you scroll past some of these cookbooks here, you're going to want to find case studies. These case studies are going to be the kind of end-to-end solutions to some of these tasks. And what we're going to do today is SFT chord receipts. So if you click on this, it'll take you to the notebook, or it'll take you to the directory. There's a little README here. This is the notebook. And you should be able to follow along. Here we go. From here, I have it locally. I'm not going to be able to run this end to end because I'm not going to make you wait 20 minutes while this thing trains, but I can at the very least kind of walk you through the steps here. So at the very top, I have some helper functions, frankly. So for example, I just want to make sure I'm getting my .env file with the right API keys that I have. This is going to use what we call the managed SFT, managed supervised fine tuning, meaning all we're going to have to do is upload our data set in the right format to the system, tell it which model that we want to use, and then what hyperparameters we want to choose. And then the Fireworks platform is going to take care of everything else effectively for us, including finding the right machines. You can also choose which machines you want, which I am going to do in this code. Helper function here, just to wait, to make sure. So if I'm waiting for fine tuning to be done, this is just a wait function. Simple helper function here to upload the data set to Fireworks, which I will show in the platform as we go. Okay, so the model we're going to do is quen vl 8b instruct. And if you're kind of doing this from scratch, if you're on the platform, for example, what you will generally do, so you're looking at the platform, if you click on the left here, models, you're going to get a category. You're going to see all the different models that we have. Here's Inkling, for example. And if you want to know which ones that you can actually work with, on the right here, you want to pay attention to these categories. So for example, I need a vision model. So we've gone from 274 to 49. I also need a model that on Fireworks at least is tunable. That's 21. So to run fine tuning on the platform with my chord receipts, I am going to need a vision model that is tunable. So from here, these are the options that I can pick from. And effectively any of these are okay to use. This is the one that I ended up choosing, this VL 8 billion instruct. Again, why? I'm familiar with the Quen family. It's a small enough model that the economics are going to work out. I'll touch on that towards the end. And from experience, I could say 8 billion parameters should be plenty to do something as quote unquote simple as a single image in and a single JSON out. Now, where I could be wrong, and I am happy to always be wrong, where I could have been wrong here is this is not enough parameters, because I showed you that JSON. Let me show you here too. It's quite a long JSON. And it does involve understanding on some level where things are, what the exactly what those prices are. And these receipts, as you kind of see here, these receipts are not very clear. So it may not have been a big enough model, but in my case, I was thinking, well, let's at least try the smaller version. I'll get through it fast relatively, and I'll be able to get a baseline score for how well it does. And I could try a bigger model from there. So I chose the 8 billion parameter model. Okay, so from there, here's our model. Now, you'll also note that I have code here to build a train and holdout set. So this holdout file, I will eventually use at the end here as our test set. So this holdout is what I'm calling my test set. So that's going to be the data set I eventually test the trained and untrained model on to see the difference. So what I'll do, scroll. Perfect. So I build my data set here. This is the slug from Hugging Face for where the data is. I also label my hyperparameters here. As I said, 6 epochs. LoRa also comes with its own set of hyperparameters. So for example, 32 refers to the rank. That is the actual how skinny, how small of a matrix should we be training. So smaller rank means fewer parameters to train. Larger rank means more parameters to train. What rank to choose will also depend on so many things. Roughly, I would say 32 or 1664, but I generally start with 32 as a rank, and then adjust it if I'm not getting the quality that I see. Learning rate, as you'll see, is a very small number. So, 1 times 10 to the negative 4 is a relatively small number. This is a pretty common starting point for a learning rate as well. Again, maybe in a future case study, I will do a sweep of all of these parameters, hyperparameters, to really kind of show how different or sometimes how not different the quality can be by changing these knobs. There's some other kind of more advanced quote unquote hyperparameters that I can set here. For example, batch size samples is something that you generally want to kind of let the platform take care of, which basically refers to how big of a batch size should this be running on. You can set this to be a number that you want, but in this case, I'm going to let the system decide the budget. What I am going to tell it though is the maximum context length that I'm going to allow. Now, you don't have to set this either. But generally, if you do set this, you'll be able to fit on a smaller machine. So here I am explicitly telling the system on what accelerator type, GPU, what GPU type that I want to use for this managed fine tuning. And then these will just name the models at the end of the day. So here I build the actual training set that I showed you before. I'm also going to include a very, very small prompt. Now, technically speaking, I do not have to include a prompt when I am fine tuning this model on the vision data set, technically speaking, because I'm teaching it to do that extraction through the data itself. But it is not uncommon to include a I mean, relatively minuscule prompt like you see here in order to kind of guide the weights along the way on what the task actually is. For what it's worth, I actually did not try this without this instruction, but I would bet that the performance would be on par even if I did not include this prompt, but I did in this case. So more helper functions to build the splits, just making sure I'm splitting up between train test splits, loading up a JSON file, making sure that they're all saved on the machine, and then I can actually get to the training. This is just going to show what the data actually looks like. So when I upload this data here, I upload this data to the platform, it's going to look like this. So this is the actual training set that I pushed up. Only 300 of them, so I didn't even use the full training set to run this experiment. Each one of these is a message list. So remember from our slides, this is going to get converted into the chat template for Quen, and then this is going to be the complete correct example, including the assistant message with the JSON in it. Once we do that, we can actually, I can also optionally set a third-party tracking system called weights and biases. In that if you are familiar for ML engineers, it is a very commonly used, free to use platform for monitoring not just the actual loss values, but also anything that you want to report, like GPU performance and GPU temperature, even things of that nature. That's optional, to be very clear, but for those ML engineers out there who are used to weights and biases, you can of course set that here. And then I kick off the job. That's it. I tell it, this data set, this model, this is what I want you to call it when it's done. This many epochs, this LoRa rank, this learning rate, these other hyperparameters. And then here, I also tell it to auto carve out a validation set. I could give it a designated train set and validation set. But one thing that's kind of easy to do is that you can just say, look, I'm giving you the full 300 rows. You carve out a validation set on the fly so that I don't have to do it for you. So either one is frankly fine. Generally speaking, I like to give my own validation sets just for the sake of total control, but this also works totally just fine as well, because all I was going to do is, in this case, randomly separate out the receipts, just like this was going to do. So then we wait, which takes roughly 20 minutes, and I'll show you what it looks like when it's done. 60 cents later, in about 20 minutes later, I get to see these loss values. So my training loss is coming down, as is my validation set. And I can also see the hyperparameters that I chose here. All the other ones it also chose for me. It also shows me my weights and biases information and all that. From here, I can deploy this model, which I do in the code, but I can also do it via the UI. And to run this supervised fine tuning, I could also do it directly from the UI as well. I would come to fine tuning. I would click fine tune a model. I would click supervised. And from here, just like in the code, I pick a model. I pick a data set. Yes, I know. You pick a model. You pick a data set. You set any. Yeah. Sorry. Just want to show you the actual. Then, not learn more. Then I can pick all those hyperparameters just like I did in my code. It's effectively in exactly the same thing. So this API version that I'm doing is exactly what I could have done on the UI. It's just you can this notebook end to end. So once this is done, I get a model back. So now all I have to do is I have to get my holdout data and define a way to see how well it did. So what I actually end up using is something called F1, not Formula One. You can talk about that as well in office hours if you want. But F1 is the harmonic mean of precision and recall. Basically speaking, it is a number between 0 and 1. And if it's closer to 1, the exact JSON that I was expecting is what the LLM actually outputted. A number closer to 0 is nothing that the AI outputted is what I was expecting from the ground truth. So it's a number where higher is better, and it's bound from 0 to 1. I deploy both of those models. So you have to deploy, depending on the model that you're using, you have to basically deploy the model. Then I will run that model against my holdout set, my test set, for the final apples to apples comparison. And when I do that, I'll come back to I'll come back to our slides here for a couple more, and then we're almost done. Is that the results that we got were actually better than I was expecting, to be quite frank, because that base Quen model at 8 billion, when I gave it no prompting other than that, that simple prompt I showed you, it got a 0% F1, a 0 F1. Not good. But that's expected. I wasn't expecting the model to know the exact format because I hadn't trained it yet. After 20 minutes of training and 60 cents, the tuned model on that holdout set got close to 90% F1. That's amazing, quite frankly, because to kind of make this as realistic as possible, I took the same holdout set and I used the base Anthropic API Opus 4.8 on the same exact holdout set, and with a better prompt. I even wrote out a prompt that would explain the format, what I'm looking for. This is an example of what it's supposed to look like. Like, I tried to actually help it as much as possible to do what I wanted it to do, and I only got 65%. Now, could I have gotten better with more prompt engineering? Probably. But the real kicker here is that if my job at my company was helping my office do this receipt parsing, I could spend a lot of my time doing this prompt engineering, hoping to get to 90+% with, again, only 300 trained pieces of data. But on the other side, I can also remind my manager, to be clear, if we want to use Anthropic, we are going to pay at least $200 if we are using their batch API pricing at night. Or if we're using their standard API off the shelf, we're going to be paying $400 to use this open model to do 1,000 receipts a day. Whereas if we fine tune this model for 60 cents going forward, it's only going to cost, and I had to give a range here depending on fluctuations. If you're only doing 1,000 receipts a day and you kill your GPU when you're not using it, that's important. You'll only pay between $55 and $75. This is monthly. I apologize. I should have written that down. To do 1,000 receipts a day would come out to roughly $55 a month on Quen, $200 a month on Opus batch, and $400 a month on Opus standard API. So for 1,000 receipts a day, this would be your estimated monthly cost. So should I use the model that's more expensive and doesn't actually get the receipts correct as well as possible, but has no way of fine tuning it with these examples? Or could I spend some time trying to get a small LLM to do the same task for me with my labeled data on cheap infrastructure and more tuned to the data that I am looking for? These are the kinds of questions you want to start asking yourselves when you are thinking of potentially entering the world of fine tuning. All right. If you've made it this far, you're a champion, you're a pro, and you're amazing. And if you want more examples from us, and we're going to turn over to Q&A in just a moment here with some questions in the chat. There are already more examples on the cookbook, like I showed you. There's also a text-only example where I do a prompt routing, where basically I'm in classifying a prompt based on its intent and difficulty to route to a specific hard or small or large model to handle it. There's a DPO example. There's even a reinforcement learning example, and I'm adding more. In fact, if you were paying attention to my cursor here, you'll probably notice that all of these. Oh, now it's drawing things. Great. If you look at these, there's even more notebooks here that I'm not going to actually show yet in its entirety because they're not done. But there's going to be plenty more examples where that came from. Cool. All right, so there's our link to the cookbook if you want it. And now it is time for Open QA, which I will remind you as I'm doing some Open QA here. A reminder, these webinars are going to be monthly, the third Thursday of every month. We have not decided what next time's topic is going to be. So as always, I'm open to suggestions. But also note, we're going to have office hours. So the office hours are going to be every first Tuesday. This is what we're aiming for, and we'll put out a calendar so that you're able to see all these events in perpetuity. So don't feel like you have to remember all this information. But more upcoming. Next Tuesday, we're going to have office hours at the same time, 10 a.m. Pacific. And again, those are going to be very unstructured. So you just show up, come with questions. I'll answer them, or I'll do my best to answer them. We can talk through some of the news, very, very informal, just making sure there's a place for you all to come find me and other members of our team to answer your questions and just chat about what's going on in AI these days. And then similarly, on July 30th, the last Thursday of the month, we'll have a Discord AMA, and you can join us there. So, all right, we have some questions coming in. Can we download the model afterwards? So I want to fine tune a model and then be able to download it. For the most part, I believe yes, you should be able to download. Now, I should be very clear. What you will be downloading is the LoRa adapter, not the actual huge model that you are fine tuning. You'll be downloading that adapter that you fine tuned, which yes, you then can use for whatever you want, whatever you'd like to do, of course. Now, ideally, we'd like you to be able to deploy that model with us on Fireworks, but yeah, for the most part, you should be able to download those adapters that you fine tune. There was a question coming in from someone asking, well, they were basically talking about their what they were trying to do. They were asking specifically, low idle serverless LoRa serving on frontier class open base models like GLM 5.2 and Inkling. I mean, generally speaking, everything that you're asking for exists on Fireworks. The idea that you have this serverless inference, and as we roll out more features in the next couple of months, we want to expand how easy it is for you to deploy a fine-tuned model. Because I'll be honest with you right now, the most consistent way that you're going to be able to deploy a fine-tuned model with us is through our really the only way is our dedicated deployment. So you'll be able to do kind of reserve dedicated compute to serve that either LoRa adapter or that fully fine-tuned, full parameter fine-tuned model that you made. Now, we also have some specific options around multi LoRa adapters where you train one base model and multiple LoRa adapters. In fact, is that a case study that I already published? He said confidently to himself and to everyone else listening, because there was not yet. Okay, perfect. I have an upcoming case study on using the multi LoRa adapter, because this is not it, right? No, perfect. It's not. So I have an example of a case study of multi LoRa adapters coming soon to the case studies. I assume the download depends on the fine tuning method. Some are not LoRa, correct? The download, if you have and I might need to double check some documentation here, but if you are running with any fine-tuned model LoRa adapter, you should be able to download it, no matter how you obtained that LoRa. For example, if it was SFT versus DPO, for example, you should be able to download that LoRa adapter. And someone was asking about some free credits, and whether or not Crow, do we have a code? You're making promises here. We do want to be able to give away credits in perpetuity. In fact, what I can definitely promise, and I'll make that promise right here live on air and recorded after the fact, we will definitely be giving away some credits at our office hours next Tuesday. If you want to show up to that, we'll be giving away some credits to try out some of our newer models, including Inkling and whatever else is generally available by Tuesday of next week. So yeah, because again, we want you to use the platform, and there's experimentation is key, but that means you're spending money on every single one of those experiments. Now, as I showed you, it was 60 cents and 20 minutes to run that one SFT. So if you wanted to do that through several different hyperparameters, you're going to be spending a few dollars here. Don't get me wrong. Question here in the Q&A. You don't train your open weight models from customers' data. How long is uploaded data retained? SOC, HIPAA? We never train first of all, we don't train models publicly. Like we don't release these kinds of models. Also, we have what we call it's what's called zero data retention. So there none of your data is being retained, let alone used for any kind of training purposes on our end or anyone else's. And that is something I will, that is something I take very proudly at this company. Is we are not using customer data in any way, shape, or form to kind of anything, let alone to train models. So just thank you for asking, because that is actually a very big deal that I want to make sure everyone knows. Maybe one or two more questions as we get to our hour and a half here, and I want to make sure everyone, at least if you're on the West Coast, getting time for lunch here. Someone is asking, I work for a VC fund and would for love for my portfolio startups to leverage Fireworks. Yeah. How can I explore a partnership for credits? Oh, just email. I'm Sanan at fireworks.ai. I'm on Twitter. I'm on LinkedIn. X. That was a habit. Email me, Sanan at fireworks, or X me, or LinkedIn message me to explore some kind of partnerships here. Your second question, what's the optimal way to get from 0 to 1? And 1 to 10 in deep learning, machine learning, engineering, core math included. I will tell you right now, one of my favorite books for this, Deep Learning Illustrated. One of my personal favorite books that I recommend for people is Deep Learning Illustrated. It is written by a wonderful person, not this guy. He's also very cute. Named John Crone. He's actually the host of the podcast Super Data Science. And I'm a little biased because he's a friend. I've been on his show a few times, but it is a bestseller specifically in the concept of teaching you the math very visually and from scratch of deep learning. So I genuinely believe it would be a very good place for you to start. One last question, folks, and then we're going to call it a day. And Crow is amazing, has already even gotten a code ready for us with $50 in free credits. So go ahead and take advantage of that, folks. One more question. Where'd it go? Any options for customers? Oh, sorry. Oh, by the way, if there are any further questions after this that we don't have time to answer live, if you are able to, again, find me or email me on LinkedIn and X and ask me these same questions, please still do so. That way we can get to all of them. But yeah, one final question here. What I just had it here from one before, because I wanted to get to it a little bit later. Which is does Fireworks recommend any fine-tuning frameworks for more advanced use cases where we would need to rent GPUs, in particular with a custom environment with our preferred harness? Ooh, excellent question. So the way to do that, and I'm going to be including more examples of that in our cookbook as well, is to use what we call our trainer jobs. So these trainer jobs are going to be kind of the most custom way that you can run a kind of reinforcement training or any kind of training job, meaning both reinforcement learning as well as supervised fine tuning, a DPO, kind of any kind of deep learning training that you can do, that you can code up that with a custom harness, for example. So you can literally train a model using an agent harness that you bring to the table locally. It does not have to be run in the cloud, for example. That is something what we call our training API, our trainer jobs on the UI. And there's going to be more case studies for that coming very, very soon in our cookbook. All right, folks. We're an hour and a half in, and I want to make sure that we're getting out of here reasonably on time. So what I want to say is, first of all, thank you all so much for being here for our first ever DevRel Fireworks webinar, talking about fine tuning with Fireworks. And as I mentioned already, if you do have the chance to find me or any one of our team members on X, on LinkedIn, or email me, again, I'm Sanan at fireworks.ai. I want to hear from you. I want to talk to you. I want to hear what you're building. I want to learn about you and what you are up to, so that we can stay in touch and I can help you and we can get you on the platform ready to go as soon as possible. So with that, I will say have a great rest of the week and have a great weekend, and we'll see you next time. Bye.